Given a binary tree of nodes, find all the ancestors of a particular node. Hi everyone, we're here today for another Exponent mock interview with Simon. For those of you who aren't already familiar with Exponent, Exponent helps you get your dream tech career with our online courses, expert coaching, peer-to-peer mock interviewing platform, and interview question database. Check it out at tryexponent.com. Okay, we're excited to have you back again, Simon. Would you introduce yourself again for our viewers?
Yeah, absolutely. So I'm Simon Ayzman, and I'm currently a software engineer at Google. Prior to my current role, I've worked at Spotify, at Etsy, Bloomberg, and Foursquare. And I also received an MBA and a master's in computer science at the University of Chicago. And I'm excited to be here.
Great. We're excited to have you. And that's such a diverse, interesting array of experience to have too.
Thank you.
Okay, so let's get right into our question for today. So the question today is, given a binary tree of nodes, find all the ancestors of a particular node.
Got it. Okay. Just so I have a little bit more clarity, would it be okay if I had some example input and example output?
Yeah, sure. If you want to share your screen, I can copy over a couple of examples.
Great. I'll do that right now.
Okay, yeah, so we have a couple of examples here. So let's say that as input, you get both the tree and the target node. So let's say that the target node that you get is 9. Then the ancestors for that would be, it's still wrong, isn't it?
I guess something like this.
This is supposed to be here, right?
Got it. 7, 3. Okay. We've rebuilt the tree based on the input and the output.
Yeah. Okay, so we have a couple of examples here. So as input, you have both the tree and the target node. So say that the target node is 9, then what the answer here would be, if we look up the tree in order, we have 7, 3, and 1. Similarly for the other example. So for the target node of 5, if we climb up the tree back towards the node, towards a root node, you have 2 and 1.
Got it. And do we want the ancestors in a list, or do we just simply want them printed out?
Either way is fine by me. You can print it out for simplicity.
Okay, yeah, I'll do that. And does the print order matter?
Yeah, so as I mentioned, you want it in order, in the order that you would climb up the tree. So basically the most recent ancestor comes first.
Okay, that makes sense. And I also noticed that we're not actually printing out the node itself. We're sort of just printing out its ancestors in order. Okay. Yeah. And are the node values themselves unique?
They might not be. You can have duplicates in the tree.
Okay. So then it makes sense that we're not really looking for a particular target value. Then we're kind of looking for a target node.
Yeah, so the reference to the node, yeah.
Yeah, okay, that makes sense. I think that the approach then that we want to take here is we do want some sort of a recursive function that will traverse the whole tree in the worst case. And basically, I think that at each step, we're sort of checking to see whether or not it's the target node that we're looking for.
Yeah, so what would the logic be if you determined that the node is not the target?
Yeah, that's a great question. I think one sort of obvious base case around this is if the current node that we're at when we're traversing is null. I think that it sort of opens up a secondary question, which is what this recursive function should actually return, if anything. Maybe I think for now, let's say we don't return anything, but I might change my mind later. But for now, we kind of have a situation where it's null. We also want to think about the situation where it's not the target when it's not null. I think what we basically want to do at each point is we want to recurse over the children nodes. And since we're targeting a specific node, it can only be in one of the subtrees at each point.
Are you guaranteed that the target node will always be in one of the subtrees of the node that you're currently recursing on?
I mean, I guess then I would ask back, will the target node always exist in the tree?
It will always exist in the tree, yeah, but will it always exist in the subtrees of the node that you're currently recursing on?
Well, I guess if we're guaranteed the existence of the node in the tree, then technically, yes. Well, okay, well, not at each step. Like we're not necessarily guaranteed that it would be in either subtree. Like for example, if we're like looking at 9, and at some point we're going to iterate over all of the leaves there, or all of the nodes there, when we would have recursed into like the roots left tree, like for example, if we're at this 2 right here, we're not guaranteed to find the 9 in either of the subtrees. So I guess I would amend my earlier statement that we're guaranteed to find the target node in one of the subtrees if and only if our current node is an ancestor. So for example, like 3, like it will always, 9 will always be in one of the subtrees of 3 because it's an ancestor. Same with 7, same with 1. But for something like 2, 4, or 5, it's not going to be in either of those subtrees. So we have to take care of that situation properly.
Yes, yeah, that makes sense to me.
Okay. So given that that's the case, I'm thinking that we definitely do want to return information in our recursive calls into the children nodes. Basically something like a Boolean for whether the target node itself is found. And if we see that it's in either subtree, that means that the current node we're at is actually an ancestor. And we want to be able to print its value, basically. So I guess to summarize, we want to do something like a post-order traversal where we visit our children first, and then based on whether it returns true from one of them, we take an action, and then we sort of bubble up those search results towards the root.
Right, and the action being printing that particular node, right? Because now you know it's an
Yeah.
answer.
Yeah,
Okay.
exactly.
Great, yeah, that makes sense to me.
All right, let's write it up then.
Yeah, great.
Okay, so get a good function name. So we're sort of given the actual root of the tree, and then also the target node that we're looking for. Let's just make it a little bit more explicit. Now, I'm probably going to have like a main function and a helper. I usually just like to write my helper functions within the initial function signature, just so I have access to everything I need. But technically, if I were to be writing this more accurately, I would have them be separate functions entirely. So I would have something like a helper where I have the current node, basically, like where am I currently at? And I want to make sure that at the very end, I simply call the helper function on the root node. So just to ensure that our function is properly called. So like I said, we want to do a post-order traversal, but first what we want to take care of is the actual base cases themselves. So, if the current node itself is none, then, we've sort of reached a dead point in the tree. We want to return false in this case because it hasn't been found. We don't want to print anything because we're sort of not there yet. However, if the current node is the target node, then what we want to do is we want to return true. Now, I don't know if printing right now is the best approach because it might not yield us the correct order. I might come back to that, but maybe I'll leave myself a comment here. Do I print here or do I print somewhere else? But I'll just leave that there as a question for myself.
Okay.
So now what I want to do is I actually want to do my recursive calls. So I want to kind of check based on my children what happens next. So did find left. We'll call the helper on our current nodes left. Actually, I think now I'm making some assumptions here, but basically what I have here is like some sort of a node class where the basic idea is I have a value, a left, and a right. So let me just very quickly initialize that just so we're both on the same page.
Mhm.
So we'll have a value, a left, and a right. And this will be something like and just to make my life a little easier, I'll add some helpers here so I can make the constructor a little bit nicer.
Mhm.
Okay, so this is what my class looks like. So basically I do a helper on the current node's left node. I also want something similar here where I do current node dot right, current node dot right. And now we have that the trigger of the rule that I was mentioning before. So if I found it, that means now that that if and only if condition comes out. If I found it in either one of them, that means that I am an ancestor and therefore I should print. So yeah, I'm gonna print the value of the current node that I'm at. So it'll be something like current node dot value and then a space just to make it a little bit clear. In fact, I'm gonna put a comma here just so it's like perfectly spaced out. And then all I want to return at the end is I want to bubble up that information to my root. So it'll be something like did find left or did find right. So basically the same condition that I have here.
Yeah.
Yeah, I think this makes sense. So I can remove this comment here. I think the ordering of this makes sense, but let's actually test it just to make sure that we have the right order of things. Okay, so let's take a look up here. So we start at the root node, we start at 1. We're not none, we're not at the target node. And let's just assume that we're doing this first case right here, this sort of longer case. So I check my left, that means that brings me to this 2 over here. We have another recursive call to the left. And at each of those points, whenever I reach a leaf node, this will return false. So from here, I'll get false. From here, I'll get false. At this point, I'll do like a check. If false or false, like none of this actually happens. So from here, I also return false. So back to this root, I will return false. Now in my right child, when I sort of get to this step, I'll do something similar. I'll check here. This will eventually return false to me. Here, on the other hand, when I do my eventual recursion, when I hit the 9, this will return true. And then at this point, I'm not printing the value of the current node when it's a target, which is right. That's actually something we noted earlier. So we're not printing 9. But when we return here, we see that this is true, and therefore we print 7. Then this bubbles back up. Then we print 3. Then we print 1. So we will have like this errant comma at the end, but I think that that's okay, unless you have an issue with that.
Yeah, don't worry about it for now.
Okay, great. So I think this looks right. I think in terms of the order, this will give us something correct. Do we want to do like an actual unit test where we like set up some nodes? It might take some finessing, but I think we can try it.
Yeah, I'd love to hear about which test cases you would specifically test this code on.
Yeah, for sure. I think edge cases are important. What happens when it's null, when the root is none, when you have only one node. You mentioned that we're guaranteed to have the target node exist in the tree, so maybe we don't have to take care of that, but maybe we could have some sort of an assertion that deals with that case. I'd also maybe want to deal with situations where the target node is like in the middle of the tree, where it's like not a leaf, just so I make sure not to print any children of that target node accidentally, because then that might I think we have that short stop right here where we kind of don't go any further, but just in case, if I was like looking for 3, for example, I wouldn't want any of these like child nodes to appear in our results.
Mhm.
I might also have something where it's like all the way on the left, all the way on the right. When it's the root, right, it should print nothing. So I'd probably have all those test cases.
Right. Yeah. I think those are all the ones that I would cover as well. So that's perfect.
Okay, great. So do we want to do one sample test case or?
Let's make sure that the code runs.
Yeah, okay, sounds good. Let's run it. Okay, so at least it runs. If we were to set up a simple case, like maybe, okay, let's node 1 equals node. Let's leave it like this. Okay, so we have our 9 nodes. Maybe we should have actually initialized them backwards because technically they'll have that information recursively. So 9 would technically point to 7, or actually no, it would be none. So yeah, that would be none. This would point to also none. So 6 is left. 6 is left. Can I hide this actually? Oh, yes, that saves me some space, a little bit easier to do. Okay, so 6 is left would basically be 8. So I'm going to initialize these first. So the left of 6 will be node 8. Oh, 3. All right, so let me just check that just to make sure. So 1 points to 2 and 3. 2 points to 4 and 5. That looks good. 3 points to 6 and 7. 6 left points to 8. And 7's right points to 9. Okay, that looks right to me. So now we just simply want to do get ancestor nodes of node 1. And the target that we're looking for is, let's say, node 9. So it would be something like this. So what I should expect to see right now is 7, 3, and 1. So let's try that out. Awesome. It did print them kind of vertically, but that looks right. Just to maybe do another sanity check, why don't we do 5, where we should get 2 and 1 in that order? Great. That's exactly what we got. All right, awesome.
Okay, cool. So in the interest of time, I'd love to move on to some follow-up questions. So I'm curious, what is the runtime currently of this algorithm?
Yeah, so I think that we have to traverse the whole tree to find the node. So I'd say that the time complexity is O of n, where n is the total number of nodes in the tree. One thing is that if the tree is guaranteed to be balanced, then in terms of space complexity, the recursive stack won't ever exceed O of log n. But otherwise, if it's not balanced, and it looks like we can't necessarily assume that, it would be O of n as well.
Mhm. Yeah, okay, that makes sense. So is there any way to improve the efficiency of this current solution?
I guess in terms of time complexity, I don't think so. I don't know if we can do better than O of n.
Yeah, you'd probably still have the same order of magnitude, but you might still be able to do some pruning.
Oh, okay, right. Yes, we can definitely prune. I don't think we can do better, like you said, than O of n, but in terms of a practical improvement, yeah, we basically want to use, I think, perfect word there. We want to prune parts of the tree that kind of we know won't give us what we need. Now, we won't always be able to prune, but one good example, for instance, is if we find the target node 5 in the left subtree of, say, the root, like at this point, we technically don't even need to search the right subtree because we've already found it.
Yes.
So the way that we would improve the code in that circumstance is let's say, I mean, let's just like initialize this to false, but the basic idea is if we did find the left, or rather if we did not find the left, we do that. Because then what that tells us is that if we didn't find it in the left subtree, we have to check the right subtree.
Mhm.
But in this case, we didn't find it, and therefore we have to do that check. So why don't we actually run this just to make sure it works? Like, we haven't broken our code in the process of trying to better it. Unit testing for the win.
Mhm.
Okay, that looks good. Let's try the 9 again, just so we see that. Great. So I think that would be one practical improvement that we've made to the code now.
And it's a pretty significant improvement because like if
Yeah.
your trees are uniformly distributed, that means you only have to search half the tree half the time. So
Yeah, definitely.
great. Okay, so that's all I had for now. You did fantastic. And I'd love to debrief a little bit about that interview. So I'm curious what you thought of it. What do you think went well, and what do you think you would want to improve?
Yeah, I think you know, at the outset there were certain aspects of the problem I wasn't sure about, like how we're going to be approaching actually getting these nodes. So I think getting some of those clarifying questions out of the way was important. I think that in terms of implementation, it was overall a pretty clean implementation. Maybe this like helper function inside of this is kind of a sight for sore eyes, so it's definitely a candidate for fixing in that sense. But I think that another aspect of it is that the code is relatively clean, but when we made that potential fix about pruning the tree, it kind of made it really easy based on how the code was written to actually make that change.
Mhm. Yeah, I think those are all really good points that I would generally agree with. I did like that at the beginning of the interview, you were able to identify the key insight of the problem, and that being that for a given node that we're recursing on, it's only going to be part of the ancestors or a node that we need to print if you can find the target node in one of its subtrees, right?
Yeah.
Yeah. And then after that, like you were able to get this entire like recursive algorithm. It's very clean code in general for traversing the tree. And I like that you had kind of like an OOP style for implementing this. So you created the separate like node class with its appropriate constructor attributes. And it'd be nice to see some getters and setters as well, but
Yeah.
that's yeah, okay. And you also did a great job of handling like all of the base and edge cases as well. Like I didn't even need to like prompt you about any of it. You didn't have any bugs there. So that was great. And I think I agree with you on the points to improve on that. This is a little bit difficult to see, but that you should always check if you're doing any redundant work, if you can somehow stop your search early for any sort of search problem. And lastly, I'm going to harp on the OOP programming again, that this function get ancestor nodes, we could actually probably implement it as an attribute of like the node class or like a tree class, for example.
Yeah, that's true.
And as you mentioned, helper could probably be renamed something else. And it's also, it's all like entirely within the get ancestor nodes function. Like there's not that much code outside of it. That's
Yeah.
So there's probably a little bit of refactoring we could do there to have like less nested functions. But otherwise, you did an amazing job, and thank you for joining us today.
Yeah, of course. Really appreciated it.
Thanks for joining us, and thanks for watching, everyone, and good luck on your upcoming interviews. Bye, everyone.
Thanks so much for watching. Don't forget to hit the like and subscribe buttons below to let us know that this video is valuable for you. And of course, check out hundreds more videos just like this at tryexponent.com. Thanks for watching, and good luck on your upcoming interview.